PreAP, PreCalculus, note section 4.1, polynomial functions that have imaginary roots. We are going to focus here at the beginning on the fundamental theorem of algebra. I know what you're thinking. How could I be in PreCalculus and just now be saying the fundamental theorem of algebra? Well, I have no explanation. A polynomial function of n degree will have exactly n roots. So if the degree is 5, there are 5 roots. If the degree is 30, there are 30 roots. Now, you might be thinking of some examples in your head that seem to contradict this, but I assure you there is no contradiction. Roots of a polynomial can be positive, they could be negative. I'm thinking, what else could there be positive and negative? They could be 0, which is neither positive nor negative, and they could also be imaginary. It's the imaginary ones that are interesting. In fact, the fundamental theorem of algebra was discovered, or I should say, was given, was stated, was invented before imaginary numbers existed. The fundamental theorem of algebra was thought of to be so important and so factual that imaginary numbers were invented to make sure that the fundamental theorem of algebra always worked. Let that sink in. Consider the two functions that follow. Answer the questions addressing both functions f and g. I'm going to trace over this for a second for reasons that we will see. If the graph is shifted up or down, what's the maximum number of zeros the graph could have? If I take this graph and I shift it up or down, shift it down, I could make this so that it has 1, 2, 3 zeros. How many turning points does this function have? So this is a turning point. That's where it changes from increasing to decreasing. This is a turning point. It's where it changes from decreasing to increasing. Another way to ask the question, how many extreme values does it have? It has 2 extreme values, has 2 turning points. Based upon the maximum number of zeros that the graph could have, what type of function is graphed? We're going to say that it's likely cubic. Likely. Why do we say likely cubic? This could be a 5th root, not a 5th root, could be degree 5 or 7. It's definitely odd, and it has at least 3 roots if this were to be moved down. And some of those, could have odd multiplicities of, bigger than 3. So we're saying it's likely cubic. On this next question, let's go ahead and assume it's cubic. Based upon the graph, identify the number of positive, negative, 0, and imaginary roots. So there's definitely one negative root right here. It's odd multiplicity because it crosses and it doesn't change concavity, therefore it's just 1. There's no positive ones. It doesn't cross at 0. I'm sorry, I wrote negative 1. Question is, how many are there? There is 1 negative root. I apologize for counting to negative 1. Now, if we think this is cubic, we've only got 1 root. There must be 2 more that we can't find, and those 2 must be imaginary. Let's look at G. I'm going to trace over this once again. First question, if the graph is shifted up or down, I'm going to shift it down. What's the maximum number of roots there could be? 1, 2, 3, 4. How many turning points does this graph have? 1 turning point, 2 turning points, 3 turning points. Another question for that is, how many extreme values? There are 3. Based upon the max number of zeros of the graph, what type of function is graphed? It's likely quartic. 4th degree. It's definitely even because the end behaviors are the same. How many positive zeros are there? There's 1 right here, and there's 1 negative 1. It doesn't cross at 0 with a y value of 0. So if this is likely quartic, that means the number of imaginary roots has got to be 2. So that concludes the fundamental theorem of algebra. The next video will talk about Descartes' rule of signs.